We're going to look at the first constructor response question. So they say that using the principles of bonding and molecular structure, explain the following statements. So we're going to do A. The boiling point of argon is negative 186, whereas the boiling point of neon is negative 246. So the boiling point of argon is higher than the boiling point of neon, as in neon evaporates more easily. You remember that whenever we're talking about boiling point or evaporation, it's definitely going to be an intermolecular forces kind of response here. So what we're going to do is we're going to talk about what kind of intermolecular forces are in neon, what kind of intermolecular forces are in argon, and then we're going to conclude based on the data. Alright, so let's read the answer I've come up with here. So you notice we're going to talk about argon first, then neon, then conclude. So here's our evidence. The strongest intermolecular force between argon atoms is London dispersion forces. So we identified the intermolecular force that matters in argon. It's also true that the strongest intermolecular force between neon atoms is also London dispersion forces. You notice that I defined these two terms up here, so now I don't have to say them again if I don't want to. And then the conclusion, the boiling point of argon is higher than neon because the London dispersion forces in argon are stronger. This is a key thing. We're using the data to conclude that the London dispersion forces must be stronger in argon. And then we give the reason why. The reason why is because argon has more polarizable electrons. So argon has 18 and neon has 10. That's more. They're in the third shell, by the way. So, you know, if you really wanted to make sure that you've got this, it'd be a good idea, just like when we're doing atomic structure, to say how many. You could say this one has 18, or they're in the third shell. That would be even stronger than what I've written here. But definitely the key things that we've noticed in the past is if you don't mention the strongest intermolecular force in each atom, if you infer one is stronger than the other and you don't mention the other, then you're going to lose credit. And always conclude by deciding which one, explaining why one is stronger than the other. Alright, so B. B is a particularly tricky one because we just don't see it very often in AP. They say solid sodium melts at 98 degrees, but solid potassium melts at 64 degrees. Now what makes this tricky, and so we're just going to start wading our way into it because we can make some assumptions here, but what makes this tricky is that we're not talking about ionic compounds, or we're not talking about covalent compounds. We're talking about metals. So a sodium atom connected to a sodium atom, which is connected to a sodium atom, and so forth. And a potassium atom connected to potassium atoms over and over and over again. And you know, the only thing we really know about metallic bonding is it tends to have that sea of electrons view. So I'm going to draw something here to show you. Alright, so what I've drawn up here is we're just imagining a whole bunch of atoms connected together. And in the sea of electrons model, we imagine that an electron is in the valence shell, and it's not really wanted because metals aren't very electronegative, so that electron can move around all throughout these, and that's what allows it to conduct electricity really well. And so you can see that in the green one here, I've kind of trying to represent sodium. Because sodium is right here on the periodic table, and you'll notice that sodium is a little bit smaller in radius than potassium. So I've drawn potassium up here indicating that the radius is a little bit bigger between the two of them, because I think that that's going to matter in our argument here in just a minute. Alright, so the first statement, since I don't really know what I'm doing here, is to just draw the conclusion from the data. Based on this data that sodium is at 98 degrees for its melting point and potassium is at 64 degrees, we can conclude that the force of attraction between sodium atoms must be stronger than the force of attraction between potassium atoms. That's why it has a higher melting point. Now you notice I didn't need to know anything about what this attraction is in order to draw this conclusion, and usually that's good enough to get a point. Now, in the second point, we got to explain why, and we want to stay away from some things. Like one is, this is not an intermolecular force that you'd see in covalent bonds because this is metallic. So we're not going to mention London dispersion forces, we're not going to mention hydrogen bonding, and we're not going to mention dipole-dipole. The other thing is, we're not going to mention lattice energy because this is not a positive and a negative. These are both sodium ions, so we can't do that. So whatever our conclusion is going to be is going to have to be based on the sea of bonding model Or the one thing we do know is what we're envisioning is these are kind of positively charged because that negative electron is leaving it. They're all sort of like a sea of positively charged atoms. And the only glue that's connecting them together is these black electrons that are flowing in and out there. That's the only thing that's holding them together. So it is a Coulombic attraction, and that's the approach I'm going to take in explaining this. Alright, so here's my conclusion, and it's all based on this idea in Coulomb's law. The Coulombic attraction between sodium ions is stronger because of the smaller atomic radius. Potassium with a larger atomic radius will have a reduced force of attraction. And so, you can kind of see that. Now, I don't necessarily, since I've got the relationship here and I've explained it here, I don't have to walk too much through the formula. Now, you might wonder, well, how the heck did I come up with this approach? And the reason is because we're just not that familiar with this. There was really no other choice, and Coulombic attraction works everywhere. We knew it couldn't be an intermolecular forces argument, so we can't go through our standard 3 steps. It isn't a lattice energy argument, although you can see that same approach about atomic radius that we'd normally use for Coulombic attraction in lattices is being used here. And so I think that's the best that we can do. Let's look at part C. More energy is required to break up a CaO crystal into ions than to break up a Kf crystal into ions. So let's start with the simple part. Since it's taking more energy, which we, by the way, know is lattice energy because these are ionic substances, if it takes more energy to break up this one, we know that the lattice energy between the calcium and oxygen ions here must be much stronger than the lattice energy between the potassium and fluoride ions. So we're probably going to, that might be a reasonable place to start, and then we'll come up with a reason why. Actually, I've changed my mind here. We're going to stick with the same strategy we always do, which is identifying the key characteristics of each compound. So let's look at them. One of the things the two things that impact the strength of this bond is the charge. If this one, instead of being +1, is +2, it's going to be stronger. If this is -2 instead of -1, it's going to be stronger. And you'll notice that Ca is a +2 ion, O is a -2 ion, and I think that's why it's going to be stronger. K is a +1 ion, and F is a -1 ion. So I don't think it's going to have too much to do with size, because you notice K and Ca are very close together, and O and F are very close together. I mean, F is a little bit smaller than O is, because it's more to the up and to the right. It's a little bit smaller, but if it were smaller, that would make the F ion have a stronger attractive force. So it goes against the data we're seeing. We don't want to do that. And same goes here. Potassium and Ca. So potassium is a little bit larger, Ca is a little bit smaller, so that would make Ca a little bit stronger. So I think, the size thing's mixed. I think it's pretty clear that it has to do with charge. So let's make that argument. Alright, so I started by just saying the features of the CaO we noticed. The charge of calcium is +2, the charge of oxygen is -2, the charge of potassium is +1, the charge of fluorine is -1. Remember, the reason we do this is to make sure that we mention both compounds. That's one of the common mistakes students make when they're answering AP questions, is they only mention one because they think this is more important. They tend to ignore that. And then let's see the conclusion. According to Coulomb's law, I'm not sure you'd really actually have to draw this out. I don't think you would. Matter of fact, there are some things in here I'll point out that I'm not sure you'd really need. But in any case, according to Coulomb's law, higher ionic charge in calcium oxide will result in stronger Coulombic attraction, causing a higher lattice energy. So this is sort of connecting the data we saw, that it took more energy to break this up. And no, you probably would not have to refer to it as lattice energy. They did not, so there's no reason you should have to either. And then you'll notice I was going to put a period right there, but I got a little bit worried because, we did mention both compounds up here, but I don't want to infer anything because I don't want to take the chance of losing credit. So this last part might not be required. So causing a higher lattice energy in CaO than was seen in the lower charged Kf crystals. You notice I re-mentioned that one. Might not be necessary, but we're just covering our bases, and it's not too long anyway. All right, and then D. So D it's a particularly tricky one, partially because if you're thinking, well, I've never learned this before, you're probably right. And you remember that most of these questions, some of these the average is going to be quite low. I think it's very unlikely that many AP students around the nation would get this one. But let's look at it. So in case they ask it on the test, we'll know it. So the first thing you got to know is when they say molten KF conducts electricity, but solid KF does not, you need to know what molten KF is. So molten is like lava, right? Molten lava. It's so hot that it's a liquid. And what that does is, unlike in solid KF, we have a lattice like this, right? And I didn't draw the extra rows, but it's very organized, it's very rigid. This negative ion stays right here, and it gained an electron from that one, and the electron stays right here. It doesn't go anywhere. But in molten KF, what can happen is these ions can start moving around because they're like liquids. They're not a crystal anymore. And as soon as you allow ions to flow, to move, that's what's required to conduct electricity. You might want to think of it in terms of like electrochemistry. If these black things that I've drawn over here are electrodes, you remember that the ions, depending on whether they're being oxidized or reduced, and that is what's happening here, they need to be able to move. So the negative ion needs to be able to move to the positive electrode so that it can donate its electron, and the positive needs to be able to move to the negative electrode so that it can donate its ion. If the ions cannot move, it cannot conduct electricity. So our argument is going to come down to essentially that. Alright, so here's my answer. The ions in molten KF are free to move toward the electrodes, a requirement to have a conductive solution. Oops, forgot my in parentheses there. And in solid KF, the ions are in a rigid lattice and therefore cannot move towards the electrode. Hence, no electricity can be conducted. Do you need the word rigid? Nope, probably not. You imply it in any sort of way, and I think the key thing here, I think all the points would be in molten KF, the ions are free to move. That's the key idea here.